All right, let's dive in. Today, we're going to pull back the curtain on the universe's official rulebook for movement, Newton's 3 laws of motion. Seriously, these rules explain pretty much everything, from why a soccer ball curves to why planets don't just fly off into space. So let's start with a feeling I guarantee you've had. We've all been there, right? You're on the bus, maybe looking at your phone, and the driver just slams on the brakes. Suddenly, your whole body lurches forward. It really feels like some invisible force just shoved you. But here's the twist. What you're feeling isn't a push at all. It's actually the lack of a force. And this is a perfect picture of what's happening. See, when the bus stops, your body wants to keep on moving forward at whatever speed it was going. It's just trying to do its thing. It takes an outside force, like your hands grabbing a pole, or much better, a seatbelt, to actually stop you. This isn't some weird fluke. It's Newton's first law right there in your daily commute. So let's really break that down. A great way to think about this first law is to call it the universe's stubbornness rule. That's because at its core, it's all about how objects have this natural, kind of lazy tendency to resist any change to what they're currently doing. Okay, here's a wild analogy for you. If a huge elephant is charging straight at you, your best move is to run in a zigzag pattern. Why? Well, that elephant has a ton of mass, which means it has a ton of this stubbornness. It's incredibly hard for it to change direction quickly. You, on the other hand, have way less mass, so you can zip and zag easily. In physics, this stubbornness has a name: inertia. So what is inertia, really? It's simply that property, that reluctance of any object to change what it's doing. And here's the key thing you've got to remember. An object's inertia is all about its mass. More mass, like our elephant, means more inertia. Less mass, like you, means less inertia. Simple as that. And that brings us to the official textbook definition. Newton's first law, which is also called the law of inertia, just says that an object is going to keep doing whatever it's doing. If it's sitting still, it'll stay still. If it's moving at a steady speed in a straight line, it'll keep doing that forever. Unless some unbalanced force, what we call a resultant force, comes along and messes things up. Take a look at this book just sitting on a table. It's not moving, obviously, but that doesn't mean there are no forces acting on it. Oh no. You've got gravity, its weight, pulling it down, and at the exact same time, the table is pushing up with an equal and opposite force. These two are in a perfect tug of war. They cancel each other out completely. So the resultant force is zero, and the book just stays put, exactly like the first law says it will. Okay, so that's what happens when forces are all nice and balanced. But let's be honest, the interesting stuff happens when they're not balanced, right? And that question leads us directly to Newton's second law, which you can totally think of as the big push equation. Ah, and here it is. You have definitely seen this one before. It's one of the most famous equations in all of science, F equals ma. It's so simple but so powerful. It just tells us that the overall force on an object, the resultant force, is equal to its mass. Remember, that's its inertia, times its acceleration. And acceleration is just a fancy word for any change in its velocity. So the law itself is super direct. You apply an unbalanced force, and the object is going to accelerate. That means it'll speed up, slow down, or change direction. And that acceleration always happens in the same direction as the force. It makes sense, right? A bigger push gives you more acceleration. But a heavier object, more mass, gives you less acceleration for that same push. Let's go back to our book for a second. This time, we're giving it a shove. Now, as we push, friction is pushing back, trying to stop us. If our push is exactly the same as the force of friction, the forces are balanced, and the book just doesn't accelerate. But the very instant our push is stronger than friction, the forces are unbalanced. Now we have a resultant force, and boom, the book accelerates. That's F equals ma right there on your desk. And we can actually put numbers to this. This is the cool part. This example shows that if you have a resultant force of 50 newtons on a 20-kilogram box, we can figure out its exact acceleration. You just shuffle the formula around. Acceleration is force divided by mass. 50 divided by 20, that gives us 2.5 meters per second squared. See? It's not just a concept, it's a predictive tool. So we've got inertia and we've got acceleration, but there's one last piece to this puzzle. Think about this. If you push on a wall, does the wall just sit there and take it? Or does it push back on you? That very question is the heart and soul of Newton's third law. Now, this law sounds easy peasy, but it's got a crucial little detail that trips people up all the time. For every action, there's a reaction force that's equal in size and opposite in direction. But, and this is the part you can't forget, the action and reaction forces always act on two different objects. Your push is on the wall's push is on you. This is a classic point of confusion, so let's clear it up right now. Look at our book again. The book's weight pulls it down, and the table pushes it up. So is that an action-reaction pair? No, no way. And why not? Because both of those forces are acting on the same object, the book. The real reaction to the Earth pulling the book down is the book pulling the entire Earth up. It's a tiny, tiny force on the Earth, of course, but it is equal and opposite. Wild, right? Okay, time for the grand finale. We're going to take all three of these laws and combine them to understand a really fascinating real-world thing. Let's talk about what it really means to fall at top speed, or as physicists call it, reaching terminal velocity. So, picture a skydiver the very instant they jump out of the plane. For that first moment, the only major force is their weight, just pulling them straight down toward the Earth. According to Newton's second law, this big, unbalanced downward force creates a big downward acceleration. They start picking up speed, fast. But as their speed increases, they start slamming into more and more air molecules. This creates an upward force, what we call air resistance. Now, the faster the skydiver falls, the stronger this upward force gets, and it starts to fight back against their weight. This means the overall, or resultant, downward force gets smaller, so their acceleration starts to decrease. They're still speeding up, just not as quickly. Eventually, they get going so fast that the upward push of air resistance becomes exactly equal to the downward pull of their weight. At this magic moment, the forces are perfectly balanced. The resultant force on the skydiver is now a big fat zero. So what did Newton's first law tell us happens when the resultant force is zero? Right, acceleration stops. The skydiver doesn't stop in midair, but they do stop getting faster. They just keep falling at that constant maximum speed. And that is terminal velocity. It's a perfect example of all three laws working together in harmony. And when you lay it all out like this in a mind map, you can really see how it all connects. The first law gives us the baseline, inertia and balanced forces. When things get unbalanced, the second law tells us exactly how they'll accelerate. And the third law reminds us that forces are never lonely. They always come in pairs. It's a complete, beautiful framework for understanding motion. So there you have it, the fundamental rules that run the universe. The question I'll leave you with is this. Now that you know the rules of the game, where can you see them being played out today? From kicking a ball to just sitting in your chair, feeling gravity's pull, physics is absolutely everywhere. Thanks for tuning in.